In this session, we're going to look at stereochemistry. So, try to understand the three-dimensional structure of molecules, learn the optical and geometrical isomerism, the master chirality, and also conformations. Then we'll tackle some exam questions. Let's get into it. So, doing stereochemistry. Alright, so when you're talking about stereochemistry, you're just referring to a 3D chemistry of molecules. So, we're saying this is a 3D chemistry of molecules. Alright, so we know that we may have same atoms, we may have same bond in a certain molecule, but we might have different 3D arrangement. And due to that, we'll discover that this is what brings about different properties. As we know that chemistry is an essential study which has led to production of many drugs in pharmaceutical industries. For example, it is used in treatment of schistosomia, which is just biohazard. You know that a drug which is used to treat biohazard is called praziquantel drug. So that drug was discovered through the exploration of chemistry. And we can talk about chloroquine, which is used to treat malaria, though this time, like in these recent years, the parasite for malaria has been resistant to this chloroquine. But we see that chemistry plays a major role in food industries, in agricultural industries, in the production of fertilizers. Other than that, it also plays a major role in mining industry, purification of copper and other minerals and all that. So this branch of chemistry, understanding stereochemistry, it is very much important because we also understand different conformations. We understand the conformational isomers, how they come about. We understand different projections like Fischer projection and also uh, many stereoisomers. Alright, so let's now look at the structure of a certain acid like lactate acid. Let's have lactate acid like that. So we can have a methyl this side, then we have COOH, then we have OH like that, then we have hydrogen. So this is the structure of lactate or lactic acid rather, which is also known as ethanoic acid. So we can determine the RS configuration. So for RS, we know that when determining RS, we must first consider which group is a bulky group. In this case, we are going to consider oxygen. So we can assign one to oxygen. Then we'll move on to a different group, which is this carbon. But you can see that we have another carbon here. So we move on to the next atom attached to this carbon. Here we have oxygen, but here we have hydrogen. So we need to consider this group to be our second bulk group. Then obviously this one will be our third. Then the hydrogen will be our fourth. So when moving, we will start obviously from the 1, then we'll move from 1 to 2 to 3 then to 4. And in this case, we can see that since we are moving in this manner, which is clockwise, so for clockwise movement, it is always R. Then for anti-clockwise, it is S. Now, we can see that our fourth group, which is hydrogen, it is in front. So we must convert, or we must do an inversion of this stereochemistry. So we'll move from R, since it was giving R, now it will be S. Because whenever our fourth group is in front, we must change the configuration to the opposite. So from R to S. So we'll say this is an S configuration. So that is what we need to do here. Then we'll look at a projection which is known as Fischer projection. So for Fischer projection, let's have a certain group like this. Then we have a methyl. Then we have our OH. Then we have our hydrogen. So for this kind of projection, we must set our eye at a certain angle. So let's say I'm looking at this angle. This is where my eye is, meaning that once I'm looking through at this compound, these two groups will be in front. So when drawing the Fischer projection, we just draw horizontal lines and also vertical lines. So we'll have our vertical line and also our horizontal line. So for horizontal line, it means that we are showing those compounds which are pointing towards you. So that is for horizontal. Then for vertical, it is those compounds which are pointing away from you. So as we can see at this compound, we have these two groups which will be pointing towards us. So for this one, these two groups will be on the horizontal axis. So we can place our hydrogen this side and also our hydroxide the other side. Then these two groups which will appear to be away from us will be on the vertical axis. So I can write that group there, our carboxylic group there on top. Then I'll have our methyl group there. So we have converted this kind of conformation into what is known as a Fischer. So this is our Fischer projection. So that is what we need to understand about Fischer projection. We just need to take note when those groups are in the horizontal axis, that is pointing towards you or towards the observer, then the groups which are in vertical axis, they're just pointing away from you or away from the observer. Then we'll look at what are known as isomers. And in this study, we'll focus more on conformational isomers. So when you're talking about conformational isomers, they are just isomers that differ as a result of sigma bond rotation, and this happens at carbon to carbon bond, which is a single bond in alkanes. So we are saying that these are isomers that differ as a result as a result of sigma bond rotation. And this happens at carbon to carbon single bond, and this is in what are known as alkenes. So that is one thing we must understand here. Then I should have to mention that there is no free rotation for atoms which have a pi bond. So no free rotation. There's no free rotation for atoms which have a double bond. That is one thing we must understand. So under this kind of conformations, we'll try to understand the Fischer projection, the Sawhorse projection first. So for Sawhorse projection, this is how you come up with it. So for Sawhorse projection, let's say you have this group, you have this compound rather, CH3, CH3. So how you draw a Sawhorse projection, just draw the carbon, then put a slanting line like that. Then on top here we attach a hydrogen, then the hydrogen, then the hydrogen. We do the same even this side. So we attach a hydrogen, hydrogen, hydrogen. So this is how you come up with a Sawhorse projection. Then we can also look at what are known as Newman projection. Okay, we can also look at Newman projection. So I'll try to draw a Newman projection from this Sawhorse kind of projection. So you can see that this is what you're going to have in front. Okay, so let me just say here I'll have my source, then here I'll have my Newman projection, then this side my source, my source projection. So let's say I have my source as I do it like that. Then I want to convert it into a Newman projection. So one thing I need to understand here is that this hydrogen is obstructing that hydrogen. The same applies with this carbon, which is obstructing that carbon there, then with this hydrogen also obstructing that hydrogen. So in short, if I have to view this molecule through this bond, which is carbon to carbon bond, so I'll place my high at this point, then I'm viewing through this bond. Okay, as I've shown here, I'm going through this bond. So this is what is going to happen. So what is going to happen here is that this group will be in front, and because it is in front, I'll denote it with just a dot like that. So this entire group will be in front, so I can denote it with a dot. Then I'll have this, like that. Then this compound or this part of the structure will be behind. Because it will be behind, I'm going to dot it with a circle. Then I'll draw my hydrogen there. My hydrogen, even there, my hydrogen. So I've shown that this is the carbon at the back, then the dot is actually the carbon in front. So by doing so, I've shown what is known as a Newman projection. Now, under Newman projection, we have two different types. There's what is known as eclipsed and also what is known as staggered. So let's look at staggered and also eclipsed conformation. So I'll have the same compound CH3 like that. So here I'm going to say staggered, then here I'm going to say eclipsed. Alright, so I'll draw my staggered configuration here. I'll start with a dot to show the carbon which is in front. Then I'll draw a horizontal line like that to show my hydrogen now. Then these slanting lines, hydrogen. Then I still have the carbon at the back, so I'll show it like that. Okay, then this is my staggered configuration, but I can draw now an eclipse configuration here. So for eclipse, I'll start the same. Okay, so now I'll have for eclipse, the adjacent groups must be close to each other. So this is how you draw for eclipse. Okay, so let me put it the other way, like that. So this is my eclipsed projection. So this is my eclipsed, then this is in staggered, and we can see that this is actually a fully eclipsed conformation. So there's what is known as a fully eclipsed and also a partial eclipsed configuration. And the other thing I need to mention here is that this staggered configuration just had to rotate. It's rotated. It's just had to rotate at 60 degrees. Then it had to form this eclipse. Then when you look at the energy in eclipse, here there is the energy between this hydrogen and hydrogen. It is 4.0 kilojoules per mole. And here Due to this steric hindrance, there is 4.0 kilojoules per mole, and also the energy which is here, it is 4.0 kilojoules per mole. And I should mention to say the eclipse conformer, when you add the total energy, it is 12.0 kilojoules. So for this one, the total eclipse conformation, so the energy give 12.0 kilojoules per mole. As we can add 4 plus 4 plus 4, that will give us the total energy, which is just 12 kilojoules per mole. Then let's look at these two kind of strain energy. So there's what is known as torsional strain, and also what is known as steric strain. So let's look at steric and torsional. So about torsional strain injury. In physics, we say torsional is that force of rotation. So even here, when you're talking about torsional strain injury, you are talking about the force that opposes rotation due to the repulsion of bonding electrons. So we are saying this is the force that opposes rotation due to the repulsion of bonding electrons. Okay, so there is that barrier of rotation, and some conformers are more stable than the other. But one thing you should understand is that the more molecules they are constantly changing into more stable. So you will find that at the same time, some few molecules are changing into unstable conformation, as more molecules are changing into stable conformations. And from our calculations, we must understand also to say that the torsional energy in each eclipse conformation is 4.0 kilojoules. So torsional energy in each eclipse conformer is actually 4.0 kilojoules per mole. So that is what we need to take note there. Then the other thing is just about steric strain, which is just the repulsive integration which occurs when the molecules are forced to be close to each other. So steric, it's that force which comes about when you force molecules to come together, and that is because of the atomic radiuses, like the atomic radii. Then for torsional, it is that force that is able to oppose rotation. So with torsional, it's opposing rotation, but with the steric, it is about molecules not wanting to be close to each other. So steric strain, it is just that repulsive force between molecules forced to be close to each other. So that is the difference between steric hindrance and also torsional hindrance or torsional strain energy. And with this one, we said it is due to the atomic radii. Okay, so that is very important for us to take note. And the other point I should mention here is that for steric strain, it is less, or should I say it is minimal, when the molecules are in staggered conformations, as I said, because when those molecules are in staggered conformations, as we do the structure, there is less steric hindrance. The molecules are not close to each other, so there is that less steric strain. But when molecules are in eclipse, as we saw with the diagram, those molecules, since the atoms are close to each other, there is so much steric strain.